Okay, so hold on. Let me get my hardware going here. Let me tell you a little bit about IR options. And here's the outline for the talk. I'd like to say that working in the beam delivery and IR area, that to a first approximation, I'd like to believe that to some extent, our choices here are somewhat independent of the accelerator technology chosen to produce the high energy. And basically, the parameters that define the IR layout are the bunch structure and the IP beam parameters. In particular, the bunch structure will determine what the crossing angle, which has a lot to say about what the IR will look like, and something about the time packaging of detector backgrounds. Bunch structure also will determine something about the feedback schemes, as Reinhard has just told you. The other side of the coin is IP beam parameters. Okay, Reinhard has also mentioned luminosity and luminosity sensitivity. I'll be talking a bit about IP backgrounds and how they generate from the beam parameters, and how these things feed into IR options, your layout choices, your site layout choices, and something of what the detectors might see. So, bunch structure versus crossing angle. In the chart on the right, we've got a number of numbers for the Tesla, JLC, NLC, and click. The fundamental reason for having a crossing angle, of course, is that the interbunch spacing in Tesla is 337 nanoseconds, whereas it's much smaller at JLC and at click. So that the distance between the adjacent bunches is as listed, either 100 meters in Tesla, 4 meters at JLC, NLC, 2 meters, say, at click. Okay. So, so basically, to deal with this fact, one puts a crossing angle into the systems with very small C tau betas. Okay, and I'll be talking about that in the next slides. At this point, I just want to say that while Tesla has chosen a 0 milliradian crossing angle, basically I think it really could be anything. It's got pros and cons, and I'll be talking about the pros and cons in the first part of this talk. Okay. So once you decide to put a crossing angle into a system, basically a number of issues come up. Generates a need for Crab cavities. There are some beam steering effects. What you have in your low radius part of your detector looks different. Your luminosity monitor looks a little bit different. Has some impact on your magnet technology. Has something to say about the distance that you might choose to use between the IP, where the interactions occur, and the first magnet, called QD0. Says something about beam extraction, and what happens with respect to beam extraction. It'll tell you something about how you're going to do beam diagnostics and how you're going to lay out your beam dumps. How you put in this angle will also say something about maybe what the maximum center of mass energy that a site can ever get to. I'm just saying here basically that you want to have a design that minimizes bends to limit synchrotron radiation. And in some sense, if you think that there's a path to the future which might involve an eventual move towards machines with higher frequencies and lower bunch spacing, there's some issue about compatibility with future designs. So why is there a crossing angle? Basically, you have to avoid parasitic collisions. You have to separate the beams so that parasitic collisions are avoided. Here we have that on the left pictorially, where basically beams hit each other before the primary IP. If you don't do something about it, if they're bunched too closely, and putting in a crossing angle takes that away. On the right side is a plot that Daniel Schulte showed at the Fermilab conference in 2000, basically showing what the loss of luminosity is here as a function of crossing angle for the click scheme for a number of different schemes, different L stars and whatnot. The basic line here is that for a very tight interbunch spacing, one would need some number about 12 milliradians or bigger. That would be their minimum. The equivalent plot for the NLC would be something like 3 or 4 down here, and the designs that we're talking about with respect to NLC and click have chosen to use a number way out here. Okay, so what does this do to the way the detectors look? I'd just like to show you some pictures of detectors to get people familiar with what things look like if you haven't seen it before. As you might know, that the American linear collider groups have 2 models: a large detector model with a 3 Tesla field and a so-called silicon detector model. From the point of view of the crossing angle, they're identical. There's an incoming beam and an outgoing beam. I guess that's all I want to say right here. On this particular plot, I'll be talking a little bit later about the masking that goes on here, the luminosity monitor, and how everything sits together inside the detector. I just want to point out on this that the choice here has been made basically to have the beams come in on one complete separate beam line and taken out on one complete separate beam line. JLC has chosen to not put such a big crossing angle in. The base of design based on 8 milliradians. And basically, for a reasonable L-star of 2 meters, there's not enough space to have 2 sets of magnets transverse. So they developed a scheme with a conventional iron magnet where basically the beam is extracted through the coil pocket of that magnet. Since that's an iron magnet that sits inside the detector, they stick it inside of a superconducting compensating magnet to keep the fields from the solenoid from affecting this magnet, and that's the way they'd like to go, or talking about going. But I think these are all parts of the options that you get to consider. Here's a picture of the Tesla IR, where basically the incoming beam comes in, and then 100 meter, half of 3/32 nanoseconds later, the other beam goes out the same aperture. So this is online, a nice big 24 millimeter radius hole for handling those beams. And with the exception of those features of beams coming in and beams coming out, basically everything else about these detectors looks the same. This is the only place in this talk where I'll have these pictures adjacent to each other. I just want to point out that you should have noticed that everybody has a conical mask, everyone has a luminosity monitor, everyone has shielding in various areas, and it's really only in this time structure that things change. Okay, I mentioned crab cavity. If you've got bunches coming in at a given angle, you still want them to collide head-on. So crab cavities are objects which basically put kicks, transverse kicks, onto these bunches so that they turn onto each other and collide head-on like that. Basically, clearly you need to have those things happening at the same time so that things align. And that constraint basically turns into a limit on what the maximum crossing angle is. So for a given technology. So basically, from my point of view, if you believe that you can make this thing work, and there's no reason to believe that you can't, you should be somewhat free to choose anything up to about that level. As the beams come through the detector sitting there with 3, 4, or 5 Tesla solenoid field, there's a transverse component to the field which will cause the beam to steer. Okay? And if you didn't do something about it, the beams would miss each other. And as a matter of fact, the energy spread in the beam would cause the spot sizes to grow up due to dispersion. Basically, however, the accelerator opticians can put do some beam steering upstream of the IP, make some very fine adjustments of the position of the final magnet, and make this all a non-problem. So while one thinks about it, it goes away right away. Once you bring the beams into collision at the IP, they continue to steer after the IP, so you've also got to do something for the extraction line. And basically there, hopefully the apertures are sufficiently large that as you change energies and whatnot, the steering will change sufficiently small that it won't be a problem either. While detectors outside this inner region are all cylindrically symmetric and on axis with the detector solenoid, clearly the need to have something coming in and something coming out will generate some non-cylindrical symmetry for the inner detectors, particularly the luminosity monitor. So this graphic is just meant to show that there'll be some design challenges in the middle. Since typically all of these things are considered to be sort of pixelated, I don't really see this as a problem. Okay. So it does affect baseline magnet technology choices. If you choose to extract outside your first magnet, basically you're trying to find something which is very compact so that you have room for it. And the NLC group has chosen to its baseline design is based on permanent magnets. They're compact, stiff, and because they have few external connections, no flowing fluids, they work well with stability ideas which are in vogue. Of course, the permanent adjustment is more difficult. And while there are schemes for adjusting permanent magnets, they're not as simple as simply turning a knob on a power supply. If you want to extract in the coil pocket, you have the complication of the superconducting tube, whereas the magnet itself is adjustable and familiar. If you choose to extract through the superconducting bore, basically you get a standard superconducting magnet, adjustable, large bore. However, it's sort of big, not stiff, and at least from the point of view of the bunch structure that we have for the X-band colliders, not as amenable to the kind of vibration suppression schemes that we're thinking about. So the Tesla design is based on a mature LHC-based design. Basically, they could build this thing tomorrow. The gradients are no problem. The apertures are no problem. It's certainly a plus. For the NLC final doublet, I said our baseline design is for a permanent magnet, and there should be no problem at all in achieving the gradients that we need and the apertures that we need in packages which are compact enough, this is the outer radius of the magnet, that those magnet pictures that I drew before would fit nicely. One of the nice outcomes of SNOMAS was the interaction between the interaction region group and the magnet group. And basically, as a result of that, there are people at Brookhaven, Brett Parker, working on compact superconducting designs based on the kinds of magnets that they built for Hera. And at this moment, in December, he came back to SLAC and gave us a complete, a complete conceptual design, vetted with the engineers for a superconducting magnet which is as compact as the permanent magnet. And so this is sort of new and on the table. And basically, where we stand now on this is, while it's got the compact, we're trying to think about, will it be stiff enough and will it be sufficiently free of connections that there not be any vibration introduced into the system. Okay, the plus part for having a crossing angle sort of begins, I would think, with the fact that once you have a crossing angle, you're allowed to have a complete devoted extraction line that can collect the disrupted beam and bring it to where you want it to be brought in a way that is amenable to diagnostics. As Reinhardt mentioned, there's an energy tail on the machine that is due to disruption, and basically the challenge is to get that energy tail through the system in a manner which is clean enough to allow for post-IP diagnostics. So the scheme that is foreseen for the NLC is to collect it, basically build a chicane into the system so that the charged particle beam is far enough away from the Beam-Strelong beam where you can put a Compton IP, an energy spectrometer perhaps downstream. Unthought of diagnostics. This is an area of work where we're crying out for experimental community to come help design these detectors, okay, and go to a dump. And basically, the apertures of these magnets, and this beamline's been completely designed, are sufficiently small that at 500 GeV, as it says down here, basically there's minimal beam loss, and there should be no problem making these detectors work. Tesla's got a little bit more of a challenge here. Basically, they extract vertically at 0 degrees, and what they do, basically, here's a picture on this side of what the post-IP beamline layout looks like. There's a series of electrostatic separators that begin at 20 meters, a shielded septum at 50 meters, and then dipoles to take the charge beam and bring it to a dump down here and off the side of the page, whereas the incoming beam is coming here, as well as the outgoing Beam-Strelong neutral beam. So basically, a lot is happening in this area, which is sort of on the 0 degree beam line directly behind the IP. You've got your septum shields, you've got your Beam-Strelong radiation, and there are, basically it's an area which is a little bit too active in some sense to be able to think about putting diagnostics right down here. So the plan there is to not worry about it and put all your diagnostics upstream. So there's been a lot of nice work done in designing a Compton-style polarimeter about 600 meters upstream of the IP, and as well to put a, I think this is a LEP-style precision spectrometer type of energy spectrometer up in that area. The American groups have talked about doing similar things upstream, but no real work has been done yet. And as a matter of fact, as I said, no real detailed work has been done on the post-IP diagnostics yet, and we'd like to have some interest generated in meetings like this to get some help. Okay, so you have to have a crossing angle. If you remember, earlier NLC designs did that by putting angles into the system. And I guess all I want to say now is that angles are bad if you want to go to high energy. This is a plot of luminosity versus energy. And basically, it's just meant to show you how the luminosity changes as a function of energy for any given IR. The main part of the curve is linear region over here, okay, where basically the fact that the energy is growing means that the admittance is getting less, and there's a natural sort of geometric increase in luminosity. This is the area that you sort of want to be in. Once you get to a place beyond that has bends that you have not foreseen in your design, the luminosity starts to roll off. If these are soft bends in the final focus and you've decided to raise the energy, and you go into your tunnel and realign things, you can flatten those things out and have a geometry change. If you have a hard tunnel that's been dug into the granite, and you can't take it out, things will fall off more quicker, and clearly it'll fall off more rapidly the higher that angle is. At the low end of the spectrum, basically, typically you'll be building your magnets with a certain size aperture. Once the beam has such a low energy that the beam size has gotten too big, you sort of run into an aperture limit, and the thing falls like E squared. So this is just another way of seeing that. This is an old plot. Basically, this was produced some number of months ago to look at the relative luminosity as a function of energy for the high-energy IR and low energy IR of the NLC design. And basically, all I want to show is that basically this design at this time had a huge 80 milliradians of bending to get the beam to IR2. And that's what's caused that rapid fall-off at 500 GeV or so. Basically, at this point, the design has been changed such that even to IR2, the angles are sufficiently gentle, 25 milliradians and gently done, that these curves lie more or less on top of each other. Okay, and so the point of this, just the standard side pictures, is just to make the point that both the NLC design and the Tesla design to the primary IR have essentially zero bending and minimal bending to get to their second IRs. So in that sense, they're both equivalent. Here's a better picture of the post-Laennec layout for Tesla, where you can see quite clearly that except for minor bends to get the chromatic correction done and to get the positron source hardware in, things are more or less straight ahead, and a crossing angle at the second IP of 34 milliradians, more or less plus or minus 17 milliradians coming off the Laennec.
10 minutes time.
Okay. Here's the same picture for NLC, where basically, in this case, the Laennecs are aligned over here and here, coming in straight to produce the primary interaction, and the angles are about 20 to 25 milliradians to produce the collisions at the second IP. That's there. I don't know why it's not there. Oh my God. This has never happened to her. It's not meant to happen. Hold on. All right. Forget it. Forget it. All right. Bitten by PowerPoint. Okay, so pros and cons of a crossing angle. People could list the cons here. You need you need beam steering corrections. You need a Krebs cavity. You have this non-symmetrical symmetry. You have a net PT to your interaction, to which advocates would say, that's easy. That's okay as long as you're below a certain limit. Who cares if it's not symmetric in the center? The converse is basically here the pros for a crossing angle, separate extraction line, IP diagnostics, easier dumps perhaps, and this perhaps allows future reduction in beam spacing, to which the other side would say, we'll solve this with pre-IP diagnostics. Dumps are fine, and who cares about the future? We'll dig later if we really need to. Okay, let me move on to backgrounds. Basically, the beam spot sizes and the bunch charges determine what happens. I guess the point I want to make is that the most important background is the incoherent production of electron-positron pairs, which I'll go into a little bit more detail in the following slides. And that the number of pairs scales with luminosity, and per unit of luminosity is equal for both designs. The detector occupancies depend on the bunch structure, and basically all of the work that's been done here is kind of work that is well suited for the experimental community to help with basically J-Hunt and Fluka style simulations. And as I mentioned before, the bottom thing says that all the IR designs are similar. So here's the beam-beam interaction. The beams are attracted to each other. Photons are produced. These photons, 1.2 to 1.6 photons per electron, take some fraction of the beam energy and go off to the dump. It's not a background problem, and basically the angular distribution of those photons, which is down over here, basically in units of milliradians, shows you that we leave a 1 milliradian aperture to handle, that's 0.2 right in that plot, to have a 5 or 6 sigma opening for that radiation to go out. Aside from that, there's no real thing. What happens is those photons, though, interact with either opposing electrons and photons to produce pairs through one of the processes listed on the left side of the equation over here, left side of the paper. What happens as the two bunches interact, those pairs are produced through these processes, and one side gets basically repelled by the charge of the oncoming beam. The other side gets trapped in it a certain amount. The number of oscillations here and the disruption in some sense depends on the length of this bunch. Okay, and basically all of the PT kick that these particles get comes from magnetic and electrostatic effects of those bunches. And there's very little intrinsic PT in here. So these things tend to be pretty soft except for something which is limited by the size of the bunch and the bunch currents. On the plot on the right, basically, the relative contributions of these processes are plotted. And the point to make here is that this is this rapidly rising one called coherently produced production, where basically the photons, the field density in the overlap field here is sufficiently high that, that these things can sort of spark out by themselves. The current designs are sufficiently below that basically these three processes dominate, particularly the Bethe-Heitler process, whereas this starts to become a more important problem at higher energies and for designs like Click. So when these particles are produced, basically they spiral in the magnetic field of the detector, hitting things. When they hit things, they produce backscattered electrons and they produce photons which shine everywhere, and that's what you have to control. Basically, as I said, the number of pairs scales with luminosity, and basically you're getting about between 1 and 2 times 10 to the 9th of these guys per second. And you control it with your solenoid field, L star, and masks. Reinhardt had a plot like this. I just wanted to say down here, for instance, that basically here are the numbers for NLC and Tesla. 1 times 10 to the 9th, 2 times 10 to the 9th. This is basically in the ratio of the luminosities. And it basically is the same disruption which is producing the 3.4 versus 2.0 luminosity numbers that's producing this. And I think basically for my understanding of all this, basically it's really the largest sigma z that gives more time for disruption that's responsible for all of this. Because this stuff is proportional to luminosity, you can use these things as a luminosity monitor, actually. And that's actually planned for. And there's been nice work originated by Tauchi and supported now by work at University of Hawaii to build the monitors that would use these pairs as a source of as a measurement for luminosity. Picture which just shows basically these pairs are produced, they spiral in the field, and they form, because they have a limited PT, because the finite size of the bunches, there's a hard edge to them. It determines what the interaction region looks like. When they get to the end, they splatter on whatever you put there. When they splatter, photons and lower energy charged particles and neutrons fall backwards. So basically, the way you design the IR is to control these guys. And basically, you do it basically by, direct hits. How do you keep the guys as they're produced from bothering you? You increase your detector solenoid field to keep them tightly collimated. You, let's say, increase the beam pipe radius so that it doesn't get in the way, and you move the beam pipe far enough away as soon as possible. That's the beam pipe in this picture over here. You move the point of first contact as far back as you can. This is the exit line over here. You try to keep the exit aperture as big as possible so that as many of these things go out and away as far as possible so that they interact in these magnets over here sufficiently away from your detector that they don't bother you. You try to keep any extraneous detectors out of this region where these particles can hit and then produce photons and particles which can shine back into your detector. So the masks, basically, the primary mask is this thing called M1. The line of motion of these pairs is indicated here in blue. And basically, you can design this mask to be anywhere along, so that its tip is anywhere along that line that you want. As you increase its length and move it in, basically, you'll be protecting your tracking chambers a bit more. But because this line is not straight but curved, rather you'll be decreasing the acceptance into your calorimeter as for that line. It seems like you need a minimum of 60 to 80 centimeters of length over here to provide adequate protection from things spraying off this front face. And that's more or less where the designs are. But the current feeling is that these things will all be instrumented and they won't cause any decrease in calorimetric coverage. Okay. Basically, this mask over here has to be thick enough that photons produced in the magnets don't shine back out. And then this piece of yellow over here basically is low Z tungsten carbon type, beryllium carbon type materials which are meant to absorb low energy neutrons and the like. So charged particle hits, okay, per bunch fall off very rapidly with radius. Let's just leave it at that. I've got numbers that are easier to see on another slide. Whether it's for NLC on this side, this is for the large detector and at the 3 Tesla field. And here it is for Tesla. Okay, photons. All right, the photon distribution tends to come. The photons that get into the central area basically come from those pairs that hit the beam pipe. And this design is a 1 centimeter beam pipe with a relatively light 3 Tesla field, so the background is peaked in the central region. The other way where particles get into the calorimeter basically is hitting the front face of the extraction line magnet at 6 meters, and they shine in because in this particular design, our shielding probably should be thicker. Okay. Basically, here's the similar thing for Tesla. Number of gametes per bunch crossing in the TPC. You're seeing that is relatively low relative to the sides because of a larger field and a larger radius. And I got that wrong. That should be 1.4 centimeters. Sorry. And things falling off the masks here. I'm out of time. Okay. All right. What I've said about the charged particles basically pertains to the neutrons as well. And basically, no, never mind. Let me just talk about detector occupancies for a second. Basically, the deal about, off the left of the slide, which is not projecting over here, these numbers in red pertain to Tesla. The numbers in blue pertain to the NLC. Basically, the readout time that I've listed here is that between the bunch trains, so that basically 190 trains, bunches need to be integrated for any given background process. So the occupancies that are listed here pertain to the VXD, say 10 hits per millimeter squared per unit of readout time in the innermost layer of the vertex detector. And I guess the point I want to make here is that for the tracking type systems where the readout times are such that the number of bunches is essentially the same order of magnitude as an NLC, the occupancies are about the same because the background scale luminosities and the luminosities are about the same. The only place where it makes a difference is in the calorimetry, where basically if you have a shaping time of 150 nanoseconds, as called out in the Tesla, you only need to integrate one bunch. That's not the case in the MCAP in the calorimeters, which are integrating a lot of bunches. This is something which needs study. All right. I want to make only one point about synchrotron radiation. I told you the biggest problem is pairs in this linear collider. At SLD and SLC, synchrotron radiation was the problem which dominated daily life in the collider hall. And basically, the reason why that's no longer a problem is that basically that the divergence angles of the beam as it enters the IP are now about a factor of 10 or more less than they are before, and the physical aperture sizes and spacings are about the same. So basically, we develop a collimation scheme such that all the synchrotron radiation produced basically goes straight out without hitting the vertex detector, without hitting anything back here. And all I want to say here, since this is the detector conference, is that basically the complexity of the collimation system is set by that VXD minimum radius. And basically, the question here is just to make sure, if you're asking for a 1.2 centimeter innermost radius, 1 centimeter beam pipe, make sure you need it, because the pain that involves goes at least as the square, if not more, of that radius. And I've heard reports recently that heard reports recently that it might not be as necessary as first thought. One of the negative connotations is basically as you collimate to get that innermost radius, you make muons. The muons are another problem. So let me just leave the muon system as that. I have 3 more slides. One just about gamma-gamma IR to say, what's the differences here? Basically, you have an IR which is very similar with a mirror system to produce the focused laser beams. There is no extraction line. Okay, basically, the divergence of the disrupted beam here is sufficiently big that nothing can be in the way over here. And so that's the reason why the crossing angle has been increased to accommodate that, and it means that the parts of the vertex detector which look down that line at your dump area over here are seeing a lot of neutrons, and have a problem. One of the things I wanted to mention, I mean, we've somehow bought into the gamma-gamma collider, and at least it appears in all of our pictures. One thing I wanted to say is that normally when the gamma-gamma people meet, they always think about producing these gammas with E minuses coming down the positron arms. And in red here basically are all the improvements in hardware that you would need, at least on the NLC positron source side, to make that happen. And they haven't really been put into the designs yet. So if people are really serious about that, there are connotations. As are, if you really wanted to, if people sometimes talk about fixed target options, the point is to think about what you need and plan for it accordingly. I I'd like to say that in summary, that I believe that the choices are still open, even though each machine has a pretty well-developed conceptual design with lots of pictures and lots of simulations. I think we're far from needing to freeze any parameter that could implicate the physics. And another advertisement here, basically, that to try to get people incorporated into all the work that needs to be done here. I think this would be part of the subject of the discussion that we're going to be having tomorrow afternoon at 4 o'clock in room 208. Thanks.
Okay, I think we have a session here on the schedule for about 10 minutes or so of questions and answers of any of the three speakers. So Chris and Rainer, could you maybe come up also in case the questions are there? I think we have a couple of microphones you can use. And I don't know, are the microphones being passed around?
I think that will be logistically hard. Why don't you just repeat the question?
Okay, fine. So then I guess we'll just throw this open for questions to any one of the three on any of the topics, or anything you want them to talk about they haven't talked about so far. Yes, Homer?
Yeah, this actually concerns the three presentations. In all three presentations, Click was mentioned independent of the lower energy accelerator that we branched onto. So the question is there any particular problem of matching onto one technology versus the other, cold versus warm? And also, how important is this, in your opinion, in terms of deciding what should be the technology of choice for a high energy accelerator? This is something that we're putting too much emphasis on now, when we know that Click may evolve greatly over the next 10, 12 years before it can actually be matched on.
Okay, the question had to do with Click. It had two parts. One was technically what are the issues in terms of matching on to that as a particular future option. The other one is how important is that? The three speakers can certainly address the first question. Why don't we see if the people want to...
Yeah, just mention something about the first question. I think the Click technology, as I showed, is quite similar in a lot of respects to the NLC in the sense of the using warm conducting accelerators and dealing with a lot of the same beam issues. And so in that sense, I think it matches very well onto the technology of the NLC. In fact, like I say, when the second half of the tunnel was filled up, when you wanted to go to 1 TeV, you could imagine at that time, if the Click technologies developed further, that you could actually do something along that lines as an upgrade. So I think in that sense, it's a good match.
Just personal opinions.
I suspect the second answer to your question is somewhat more subjective. So.
Just requesting an opinion, that's all.
Yeah, no, like I said, I think it's the big selling point there is this expandability, and once they prove that, I think it will be used if it works as advertised.
Okay. Other questions?
To the left, Dave.
I'm sorry. Yes. Okay. Ron. Chris, why don't you stand in the microphone?
Tom, one of the selling points of this machine is going to be the fact that if you run, say, at some energy like 500 GeV, and say you don't find anything new except maybe for 116 GeV Higgs and nothing else, and then one of our selling points is the fact that we can do very high precision measurements, comparison with the standard model, and really extend the discovery potential of this machine by an order of magnitude above the center of mass energy of the machine. So in order to do that, the detector has to be really well calibrated and really well understood. And as we have learned from LEP 2, for example, running at the Z peak in order to calibrate detectors or recalibrate detectors or understand this is a very important component. So in this high energy option of the American designs, the question is if you're having something like 500 or 800 GeV or whatever as your sort of your IP layout, and you want to do some running at the Z peak, then what is going to be the luminosity? Is it going to be enough to be able to calibrate your detectors well in order to do these precision measurements?
The answer is yes, basically. The design incorporates the belief that calibration at the Z is necessary no matter what the IP is.
Okay, but I mean, the curves you're showing showed very small luminosity, like 10 to the 30 or something, and that. But I mean, Chris, that which is not enough. And but I mean, on the other hand, there's this development you were talking about. The fact that there now is a superconducting version which is being developed, which might work. It probably would improve that a lot.
I think it would improve it, yes.
Okay.
And we're certainly very excited about that.
People follow the discourse up here? Okay. Paul, did you have a question? Yes. And then Dan.
I just wanted to clarify the conversion of a E plus E minus collider into a gamma-gamma collider that Tom was just talking about. It sounded as if you mentioned a modification to the crossing angle, to removing elements in the extraction line in addition to the introduction of the E minus capabilities in the whole injection. All of that is necessary in order to go
That's correct. Basically, the 20 milliradian crossing angle on the primary IP is meant to keep parasitic collisions from bothering you. The crossing angle at the other IP can be any number between, in the case of NLC, say, between 4 and 40. 30 has been chosen as a number which our gamma-gamma friends say is compatible with their design so that the disrupted primary beam can get out and not hit anything close to the IP. Unfortunately, its spread is so large that there's not an extraction line that can accept it and do anything with it. So the plan is, right now, much more work needs to be done to just take that stuff down a tunnel far enough away that it doesn't bother the detector or bothers it minimally.
Is there going to be a talk on that in one of the sessions tomorrow?
Not particularly. It's a physics session.
In the physics session, okay. So anyone listening? Dan, you had a question?
Yeah.
Oh, I think you got a microphone.
So in Paul's talk, he presented a nice list of some of the technology outreach options, such as the light source or a nanostructure facility. And I'd like to know from the machine guys, besides the light source option at Tesla, which is obviously highly developed and we hear a lot about, what other kind of thinking, if any, is going into these other kind of lines, which will be important for, you know, embracing, for being embraced by the larger scientific community?
Can you handle that, Dave?
Maybe I had answered that question. It's probably directed more at me. I think, first of all, the Tesla group has done a great deal of work, of course, as you know, in trying to understand that work. And in our laboratory at SLAC, there is a project, the LCLS project, which is an S-band linear coherent light source, which is, we think, a very important first step to understanding exactly what you really have to do to make these things work. A number of the people who work on NLC actually work on LCLS as well. We understand what's happening there. And that was a project which is already into the first approval stages. And we expect to learn a great deal from that and let that feed back into the way we would think about that in terms of a facility for the NLC. I think the answers are going to come from that relatively quickly, as a short bunch pulse facility is actually installed in the SLAC LINAC in the coming year. And looking at very short bunches will teach us a great deal. So we think there's a large overlap in that work, and we look forward to actually getting answers back from that first facility in the next coming years, which will teach us a great deal about how to extrapolate that into the X-band machine. But certainly nothing in the case of the NLC layouts precludes the use of that piece of the LINAC for accelerating beams, extracting them out, and then putting them into an FEL. The other issues that Paul raised were very interesting, of course, questions about radiography on work of that sort, and that's something that people haven't thought at all about, and would be very welcome to hear an awful lot of thought about that from people who reach out to that. So I think that's a very good suggestion from Paul. Is that an answer to your question? And I think we're really trying to get at it, a real X-ray FEL at SLAC, and understand exactly how it will work and get the information we need to know how to actually work with those short bunches. It's a very tricky business with that short a bunch. Young-Ki?
Yeah. In Japan, they already approved the FEL in proton. So they take that as separate.
Yes. Young points out that also in Japan, the Spring 8 FEL is based on a C-band accelerator, and in fact, there's a large overlap there between the development of the C-band RF system, which is already committed, to use for the FEL at Spring 8, and that's a project also that's approved and underway, too.
We'll have another opportunity after the 5 o'clock session for this kind of discussion, so maybe...
Do you want to cut off? Sure.
Yeah, I think, why don't we call it closed down, take 20 minutes for break, and start the next session 10 minutes late at 11:10.